Hello again, everyone. We're back with another lecture of C++ real-time audio programming with Bela. Today, we are going to be talking about filters. Filters are simultaneously one of the most important aspects of digital signal processing and also one of the trickiest for audio programmers to implement. The reason is that filters can be quite mathematically complex to design. To go from a set of specifications to a set of equations that implements a filter is a topic that you can spend considerable time on in a digital signal processing course. We are not going to cover this aspect of filter design today. There'll be some references that you can find in the companion materials if you want more details about coming up with filter equations. Instead, we're going to look at the question of taking a filter design and implementing it as working code. So if you were given a filter equation that you have designed from some other source and you want to know how to write real-time audio code that implements that filter, that's what we'll cover in this lecture. We will, as always, be working with Bela to implement our filters, but of course these principles can apply to many real-time audio processing environments. In this lecture, then, you'll learn some basic theory and terminology of digital filters. We won't go into the mathematics of filter design, but we'll cover enough terminology for you to be able to analyze a design and turn the equations into working code. By the end of this lecture, you'll make a few simple filters, culminating in an adjustable resonant low-pass filter. As always, you can find the companion materials, including the code examples, at the GitHub link at the bottom of the screen. To follow along with these examples, you'll need a Bela starter kit or a Bela mini starter kit. Either will work equally well. At the very end of this lecture, I'll show you how to control the parameters of your filter using Bela's analog inputs and potentiometers. That will require a breadboard and some jumper wires. However, you can control the filter equally well with Bela's built-in browser-based GUI, so no electronic components are strictly required for this lecture. Let's start with the basics. Filters are one of the fundamental tools of digital signal processing. They can alter the magnitude and the phase of different frequencies in your signal, and they're widely used in audio. You'll encounter many different filter types, many of which may be familiar, including low-pass filters, high-pass filters, and band-pass filters. Some less common but equally important filter types include peak-notch filters, shelving filters, and all-pass filters. The last of these doesn't change the magnitude response of any frequencies, but alters the phase, which can be very important in certain applications. What kind of filter you have largely depends on the mathematical equations. The principles that we're going to see here today of turning equations into code will apply equally well for any of these types of filters. One thing it helps to know for this lecture is the decibel scale for amplitude. Decibels were covered in lecture 4 of this series. It's essentially a logarithmic scale for expressing the ratio between two quantities. The formulas to convert from linear ratios to decibels and back again are shown here. The reason it's useful to know this for filters is that we often use decibels to talk about the filter magnitude response. For example, the critical frequency, or cutoff frequency for many types of filters, is sometimes given as its -3 dB point. What that means is that if we have the filter magnitude response plotted in terms of frequency, the -3 dB point is the frequency where the filter response is down 3 decibels compared to its passband. We'll talk more about that term in a moment. Given the formula above, how would we express -3 dB as a linear ratio? Well, we would take 10 to the power of -3 divided by 20. That computes out to about 0.707. More precisely, we're often interested in where the response of our filter drops by a factor of the square root of 2 compared to its passband. Okay, what do we mean by passband? Let's start with some terminology. This refers to the region of frequencies that the filter passes relatively unchanged. We can contrast this with the stop band, which is the region of frequencies that the filter largely blocks. The transition between the passband and the stop band is known as the cutoff frequency of the filter. The cutoff frequency of the filter is typically given as its -3 dB point, as we talked about a moment ago. Notice that doesn't necessarily mean the filter has a raw gain of -3 dB at the cutoff frequency. All it means is that the gain is 3 dB lower there than it is in the passband. So the example filter we see in the plot here has a cutoff frequency of f. Here's an example of the same filter with a cutoff frequency of 0.1 times f, or 10 times f. You can see that they have the same shape, just shifted up and down in the frequency spectrum. And notice that this plot is a log-log scale, logarithmic in terms of frequency and also logarithmic in terms of magnitude, which is why we are specifying it in terms of decibels. The filter we see here is a low-pass filter. For other types of filters, such as bandpass or peaking filters, we might talk about its center frequency rather than its cutoff frequency, but the basic idea is the same. Another important filter term to know is bandwidth. For any filter with a peak, the bandwidth describes the width of that peak. So here we have a simple bandpass filter, and the bandwidth is measured as the difference between the two frequencies where the gain is 3 dB less than the peak. We can also talk about the Q factor of a filter. Q is mathematically defined to be the center frequency of the filter divided by its bandwidth. In other words, the narrower the bandwidth, the higher the Q. The bandpass filter we see in the plot here has a Q of about 0.7. We can also talk about the Q of resonant low or high-pass filters, like this one. The Q here describes the sharpness of the resonant peak around the cutoff frequency. So here we have a Q equal to 3, a Q equal to 6 will have a sharper, higher peak, and then we can see some other examples of progressively lower Qs. Notice that each of these has the same critical frequency of F, but a different amount of peaking. Finally, a useful term to understand is the order of a filter. The filter order tells us how steep the roll-off is in the stop band. Here again we see the pass band and the stop band of this filter, and the minus 3 dB point, which defines the cutoff frequency. For a filter order of n, the roll-off is defined to be 6n decibels per octave. In other words, for each doubling of frequency, the magnitude response drops by 6n decibels. Alternatively, we could specify it as 20n decibels per decade. In other words, when the frequency goes up by a factor of 10, the magnitude response drops by a factor of 20n. This particular example has a filter order of 2, so we can call that a second order filter. Its roll-off is 12 dB per octave or 40 dB per decade. We can contrast that with a first order filter, which is 6 dB per octave or 20 dB per decade, or a fourth order filter, for example, which would be 24 dB per octave. Each of these filters has the same minus 3 dB point, but a different steepness of roll-off in the stop band. When we implement discrete time digital filters, the order is given by the number of taps that the filter has. A tap is a previous input or output which is used to calculate the current output of the filter. We'll talk about that shortly. The filter shown in blue here would use the current input, the previous 2 inputs, and the previous 2 outputs to calculate its output value. In this lecture, we'll only look at implementing filters up to second order, and that's because a useful mathematical property of higher order filters is that they can always be built out of simpler, smaller sections. One last bit of terminology before we get into filter equations is to understand how frequency is represented with digital filters. When we operate in the continuous time analog world, we represent frequency in hertz, which is cycles per second. By contrast, in discrete time, we have a formulation for frequency which might be unfamiliar. Frequency in discrete time is normalized between 0 and 2 pi, where 2 pi corresponds to the sample rate. For example, the Nyquist rate, which is half the sample rate, would correspond to a frequency of pi. It's useful to know this frequency scale in case you need to pass it into any discrete time filter design equations. The other thing you'll typically see with discrete time filters is a mathematical representation in the frequency domain. This is based on something called the z-transform, where z is a complex number. I'm not going to get into the mathematics of this here, but there are lots of good DSP references, some of which I'll post in the companion materials. The idea is that we can represent complex numbers in a two-dimensional space according to their real and imaginary components, and within this two-dimensional space, frequency between 0 and 2 pi is mapped to the unit circle, that is to say the circle with the radius of 1. The formula that gives us this mapping is e to the j omega, where j is the imaginary number, sometimes also called I, and omega between 0 and 2 pi is the discrete time frequency. So, for example, a frequency of 0, or dc, would be located here on the unit circle. E to the j0 is equal to 1. The Nyquist rate would be a frequency of pi, and e to the j times pi is equal to -1, so it's there on the unit circle. Or half the Nyquist rate, a quarter of the sampling rate, which has a discrete time frequency of pi over 2, would map here on the unit circle to a frequency of j. The reason this is useful to know is that you'll oftentimes see the frequency response of a discrete time filter given as h of z, and you can just plug in z is equal to e to the j omega for the frequency of interest to find out its magnitude and its phase. Let's now look at the filter equations themselves. The typical filter equation specifies a linear time-invariant filter. Linearity and time invariance are properties of signal processing we won't talk about more here. Generally speaking, a discrete time filter can be specified by its coefficients. What this equation says is that the current output y of n is given by a weighted sum of the previous outputs y of n minus k and the previous inputs x of n minus k. So the coefficients b sub k specify the weights of the previous inputs, and the coefficients a sub k specify the weights of the previous outputs. Now, how you go from filter specifications to these coefficients is the topic for a DSP class that we're not going to cover here. Our interest is, given this set of coefficients, how are we going to implement this equation in code? What we'll need to do is for each new sample, we'll need to recalculate the equation above and we'll need to update the previous inputs and outputs. An intermediate step that can be useful to understand filters is the block diagram. So this equation here could also be specified as a block diagram like this. In fact, there are multiple mathematically equivalent block diagrams for implementing the same filter. But let's look at the component pieces here. The input signal is on the left, the output signal is on the right. The arrows indicate the direction of signal flow. The triangular blocks indicate gains or multiplications by the coefficients. The blocks labeled z to the minus 1 indicate a unit delay. In other words, if the signal coming in is y of n, the output is y of n minus 1. Given that, what would be the signal at this point after 2 unit delays? Well, the answer is that it would be y of n minus 2. Finally, the circular plus symbols are our summing junctions. They simply add together each signal coming in. Now, for any filter that depends on both previous inputs and previous outputs, we describe it as an infinite impulse response, or IIR filter. What that means is that this filter uses feedback, and because of that, if we ping it with an impulse, which is a signal that is 1 for one sample and 0 ever after, the output will never actually return exactly to 0. Every continuous time filter in the analog world is IIR. By contrast, if a filter depends only on its previous inputs and not on any of the previous outputs, we can describe it as FIR, or finite impulse response. What that means is that when we put an impulse into the filter, eventually the output will return to 0 after a finite number of samples. So in this case, the FIR filter begins with a similar block diagram to the IIR filter, but because the a sub k coefficients are all equal to 0, we can simply neglect that part of the signal chain, leaving us with a simpler output. FIR filters are quite useful in a number of different digital signal processing applications. Before going on, I want to emphasize that everything in these block diagrams is completely generic. This does not tell us whether a filter is a low-pass filter or a high-pass filter. It applies equally for different orders of filter, and in fact, any linear time invariant filter can be implemented according to these equations and diagrams. Having said that, let's now turn our attention to implementing a very simple filter in code, which will reveal some of the challenges of doing so. The filter we want to implement is called a first-order difference. Y of n is equal to x of n minus x of n minus 1. In other words, the current output is the current input minus the previous input. The first question is whether this is an FIR or IIR filter. Well, because there's no dependence on the previous outputs, it's FIR. Now let's ask a slightly trickier question. Is this a high-pass or a low-pass filter, and how would we know? Let's start with the intuitive explanation. Consider what happens if your input signal x of n has the same value for all n. Well, in this case, you can see that x of n minus x of n minus 1 would always be equal to 0. In other words, a DC signal, which is the lowest possible frequency, would be blocked. But we could also answer the question mathematically, using the z-transform. Again, I'm not going to explain how the z-transform works here, we'll just use its outputs. For this particular filter, we can write h of z is equal to 1 minus z to the minus 1. And rearranging, that gives us z minus 1 in the numerator and z in the denominator. Notice that if we plug in z is equal to 1, h of z is equal to 0. Well, what frequency does that correspond to? We saw earlier that frequency was mapped to the unit circle, so z is equal to 1 corresponds to omega is equal to 0. In other words, this filter blocks low frequencies, therefore it is a high-pass filter. Here's the general block diagram for implementing an FIR filter. What we need to know is what our coefficients are. Well, our coefficient b0 should be equal to 1 because that's what multiplies x of n. Likewise, we're subtracting x of n minus 1, so b sub 1 should be equal to minus 1. And that means that we can simplify the block diagram into just this that we see at the bottom. This brings us to our first task. In the companion materials, you'll find a project called Sample Player Filter. What this does is it plays a sound file in a loop. The filter isn't implemented yet because that's up to you. Inside of Render, your task is to implement the filter given here. And potentially the trickiest bit about this is to figure out how you're going to keep track of the value x of n minus 1. Remember, we found that this was a high-pass filter, so you should know that it's working when the base frequencies are reduced in the output. The question is, what information do you need to keep track of to implement this equation? We know the coefficients, of course, but we also need to keep track of the previous value x of n minus 1. We've seen in previous lectures that anytime you need to keep track of something that happens in the past, we need to use a global variable to do that. So be sure to add a global variable to this project and implement the equation inside of render. Pause the video here. Let's look at the critical bit of this code. At the top of the file, you should have declared a global variable. It needs to be a float because it needs to hold fractional values, and it's important to initialize the variable to 0 so you don't have any artifacts when you start the program. Then inside the render function, we'll have our usual for loop that goes through the number of audio frames. And let's start from the end backwards. Notice that after we've made the calculation, we are going to take the current input and we're going to store it inside of glastSample, so that the next time around the for loop, glastSample represents x of n minus 1. We talked about this same idea in the previous lecture in the context of detecting button presses, and we'll look at it more in a moment. We can see that the equation itself then is relatively simple. We just set the output equal to the input minus the last sample. To understand why this recursive strategy works, let's consider what value each of the variables has as we step through the for loop. In the beginning, we'll start with an index n is equal to 0, and the variable in will hold x of 0. At this point, glastSample will still hold its initial value of 0, and the output will be x of 0 minus 0. By the time we get to the end of the loop, in is still going to hold x of 0, but glastSample will now have been updated to be equal to x of 0. Therefore, when we begin the second time through the loop, when n is equal to 1, in is going to be equal to x of 1, but glastSample is still going to be equal to x of 0. That means that we can calculate our output of x of 1 minus x of 0, as we want. Again, by the end of this loop, the value of in won't change, but glastSample will be updated to be x of 1. The output won't change, but that means that the third time through the loop, the input will be x of 2, glastSample will be x of 1, the output will be x of 2 minus x of 1, and so forth. And in this way, we keep track of the previous input and we're able to calculate this simple high-pass filter. Here then is the code in context. You can see that our global variable is declared here, and then down inside of render we have the code that we saw a moment ago. Once we calculate the output, then we are going to write it to each of the audio channels using the audio write function. When we run this code, we'll hear that the drums are now high-pass filtered. There we go. Before moving on, let's just have a quick look at where this audio playback is coming from. You can see that the input signal comes from this object called gPlayer. Now this is an instance of a class called monofilePlayer that I have declared over here. What this basically does is that it encapsulates the audio buffer playback routines that we saw in Lecture 2 into a simple class. Here inside of setup, it will load a sound from a file, and we have control over whether that sound plays in a loop or just once, and whether the sound starts automatically. If the sound doesn't start automatically, then we can call this method called trigger to start it playing. The method called process is one that we saw in our wavetable example from an earlier lecture. The idea of the process method is that we call it every single audio frame regardless, and it will return to us the next sample in the buffer. If we go over to the CPP file that implements this, then we can see down inside of the process method. Inside the process method, we essentially have the same code that we would have seen in Lecture 2, where we read a sample from a buffer, we increment our read pointer, we check if the read pointer has gotten to the end of the buffer, and if that's the case, we either reset it back to 0 and start playing again, or in this case, if we only want to play the sound once, we set this flag is playing to false. That means that the next time we call process, we will just simply return and not play a sample. And of course, the monofilePlayer class is very simple. It doesn't do things like playing multi-channel files, it doesn't give you many transport controls, but hopefully in looking at this, you can see how you might extend it for your own code if you were interested. Let's look at a slightly more complex example. This time, we're going to implement a filter starting with its frequency domain representation h of z. In this case, that's defined as y of z divided by x of z, and that is 1 minus alpha over 1 minus alpha times z to the minus 1. We can rewrite this using some basic algebra, and then we can use the z-transform to turn this from the frequency domain into the time domain. With a bit of rearrangement, we get an expression for the output y of n in terms of the previous output y of n minus 1 and the current input x of n. Again, the mathematics of what just happened there are well covered in other sources, and I'll post some links online. Suffice to say that we are looking at a first-order IIR low-pass filter. We know it's IIR because it involves the previous output y of n minus 1. We know it's first-order because n minus 1 is the earliest sample that is involved. And we could work out that it's low-pass based on evaluating the equation at the top. Now, if you took a moment to do that, you might figure out what kinds of values of alpha would be useful to get a very low cutoff frequency. I'll spare you the derivation and just say that values of alpha close to 1.0 but strictly less than 1 will be good ones to try. For example, when you implement this in code, I suggest you try alpha is equal to 0.99. So this is your next task. In the same project that you just worked with, implement this filter instead. You'll need to keep track of a slightly different bit of previous information as compared to before. See if you can work that out. Because this is a low-pass filter, when it's working you should hear the bass components of the drum loop, but not the high-frequency parts. Let's look at the completed code then. I've declared two global variables. The first of them I'm going to use to hold the previous output y of n-1, and the second is my coefficient alpha that we saw in the equation. I've set that to a value of 0.99, though you can experiment with different values. We'll go down to the render function, and we will see that, as before, we get our input signal from the gPlayer object, and our goal is to calculate this equation. That's implemented by this line of code. Float out is equal to g alpha times g last output plus 1.0 minus g alpha times in. And of course, the critical piece to making this work is to set g last output to be equal to out. We set it to out rather than to in like before because we want it to hold y of n-1. So when we run this example now, you can hear that we have a low-pass filter in operation. Now let's try something a bit more complex. We're going to implement a general second-order IIR filter, sometimes called a biquad. The idea is that the code that we implement here could be used for lots of different filter types, low-pass, band-pass, high-pass, etc., and it's just down to which coefficients we have. Now, regardless of the coefficients, we need to know how many previous values of x and y do we need for a second-order IIR filter. The answer is that we need two each. We need x of n-2, x of n-1, y of n-2, and y of n-1. So how many global variables are we going to need for all that? Well, of course, that would be 4. How then do we keep track of the samples that are 2 frames old for x and y, x of n-2 and y of n-2? This is maybe slightly trickier than keeping track of x of n-1 or y of n-1. What we're going to need to do is have a sort of recursive strategy where we're going to take the sample that used to be x of n-1 and copy it into the variable that holds x of n-2, and similarly with y. And of course, like before, we do this at the end of the loop after we have calculated the output. One particular thing to be careful about here is the order that you move the current samples to the previous ones. So let's say that we have our values of x, and we have x of n-2, x of n-1, and x of n. And these colored rectangles represent different values that I have stored. What I want to do is when I'm done calculating the output, I want to throw away the oldest value, x of n-2, and I want to move x of n-1 into its place. Once I've done that, then I can move x of n backwards into x of n-1, and that lets me store the current input, which will now be there for the next time around the loop. What we don't want to do is this. Suppose that we have these 3 values, and we start by taking x of n and putting it into x of n-1. Well, now look what's happened. We've overwritten the old value of x of n-1, so when we try to put that into x of n-2, we just end up copying the same sample into 2 different slots, and our filter won't work correctly. So the order of your code really matters here. In the next task, you have a project called resonant lowpass. This is a special case of a second-order IIR filter that implements a low-pass filter which has a variable Q that you can use to make a resonant peak. Resonant low-pass filters are commonly used in modular synthesis. The equations for calculating the coefficients are already given to you, and I'm not going to talk about those here. Your goal is to take those coefficients and implement the filter calculations inside of render. You'll need to declare the global variables that you need to remember the previous state, and you'll need to manage them inside of your for loop in render. Once you've got it working with the default set of coefficients, then I suggest that you add the ability to control the frequency and the Q. What you can do is by calling calculate coefficients inside of render, you can update the coefficients which will then be used in your code. You could use either the GUI controls or the analog inputs to do this, following what we've seen in previous lectures. I'll show you examples of both when we're done. One word of caution before you work on this is that you'll encounter different conventions for the sign of the A coefficients which multiply the previous outputs. Sometimes you'll see the current output expressed as the sum of B sub k times x of n minus k plus the sum of A sub k times y of n minus k, and sometimes you'll see the A coefficients inverted. y of n is equal to the sum of the b sub k's times x of n minus k minus the sum of the a sub k's times y of n minus k. The latter is how it works in this particular example. You can always work it out mathematically, but sometimes it's pretty easy just to try it both ways and see which way works. Pause here, try this. You'll be able to tell that it's working because you'll be able to change the tone of the guitar by changing the frequency and the Q of the filter. Alright, here we are with the completed code. As before, we are loading a sound from a file, this time a guitar sound sourced from Freesound. You can find the link in the companion materials. And again, we're using the monofile player object to play it in a loop. This example is going to use the GUI to adjust the filter parameters. We have a set of global variables that we are using to keep track of our previous inputs and our previous outputs. We likewise have a set of global variables to hold the coefficients which were given to us. The calculate coefficients function was already given to us. We don't actually need to change that. What we need to do, though, is implement the code inside of render. So if we scroll down there, we can see that this is the critical equation. This implements the output as a weighted sum of the current and previous inputs with the b coefficients, and then subtracting the previous outputs weighted by the a coefficients. And then crucially, this is the part that updates our previous state. Notice that we are setting x2 is equal to x1 before we set x1 equal to the current input, and the same thing with y2 minus y1, and y1 being equal to the output. It doesn't matter whether you update the x or the y first, but it certainly matters that x2 comes before x1 here. At the top of render, then, we have the code to get the current parameters from the GUI. We've seen this in previous lectures, so I won't go over it in detail. We pass those values into the function calculate coefficients. Notice that we're only calculating it once per block rather than once for every audio frame. In addition to the fact that the GUI can't update more frequently than that, that also saves some computation, because calculating the coefficients is more computationally expensive than applying the filter. So I can run this example now. You'll hear the guitar playing, and it's low-pass filtered already using the default values that were given at the top here, which is a frequency of 1 kilohertz and a Q of 0.707. Now I can open the GUI, and we'll see these controls that I can now update. I'll start by increasing the Q, and then I can change the frequency up and down. Alright. You might hear that what we're doing is very similar to a wah-wah effect, and in fact that's basically exactly what a wah-wah pedal is. It is an adjustable filter with a high Q to provide a resonant peak. Now let's look at the example involving the analog inputs. In this particular case, the filter calculation is the same as before, as is the code updating the previous state. What's changed is where we get the parameters from. We're using the analog read function, which we saw in lecture 6. This reads one of the analog inputs, which is given by the third argument here. So this is equal to 0, and this is equal to 1 declared at the top of the file. In this case, the parameter of 0 just says read the first analog frame in this particular call to render. Again, we're only going to update the filter coefficients once per block this time, rather than once for every audio frame, even though we could do that with the analog inputs. What follows then is some equations to map the analog inputs from 0 to 1 range to a more useful range for frequency and Q. The Q is relatively straightforward. It uses the map function, which we've seen before. The frequency calculation looks a bit more complicated. That's mainly because I'm doing a logarithmic mapping following some of the principles that we've seen in earlier lectures. Anyway, if we run this, we should be able to hear the sound in action. Now the first thing I'll do is I will increase the Q a bit so we can hear the resonant peak. And then I can change the frequency up and down. And there we go. For details on how to wire up that circuit, see Lecture 6. Just a few words about DSP theory as we wrap up. Generally speaking, the digital IIR filters that we use are almost always designed based on analog prototypes, and so there are some useful equations for converting continuous time filters into discrete time ones, which is what we're effectively doing here. One tool is called the bilinear transformation. The way it works is that we start with a continuous time frequency domain transfer function, h of s, and then what we're going to do is perform a substitution where s is equal to this formula involving z and t, which is the sampling period. Having made this substitution, we can then write out an equation in the z-domain for the digital filter. And having done that, we could use the z-transform to convert that into a difference equation that we could implement in our code. There are several very good tutorials on how all of this works, including Julia Smith's online textbooks, one of which is linked here. I'll also note that Bela provides a built-in library called biquad, which implements a number of different common second-order filters. This, in fact, is based on other open-source code by Nigel Redman, and details on that can be found in the comments in the library. That brings us to the end of this lecture. As usual, be sure to click subscribe so you're notified of all the new lectures as they become available. You can find us on social media or at a number of web resources that we have available here. Thanks a lot for following along. See you the next time.